who will talk to us about compatibility of T structures in a semi-orthogonal decomposition. So when you're ready, Antonio.
Okay, thank you for the possibility, and also thank you for organizing this event. I'm finding it very, very interesting and fascinating. So my presentation is called The Compatibility of T Structures in a Semiorthogonal Decomposition, exactly as the name of the preprint you may find in archive. And well, I will talk about triangulated categories. So the framework will be this one, and we will try to study triangulated categories via exceptional sequences. Afterwards, we will see the notion of compatibility, which will help us to use exceptional sequences to get to the main theorem. So without further ado, let's go to triangulated categories. What are they, first of all? And let me say something very roughly. So triangulated category is something resembling an abelian one. So you are kind of try to replace kernels and co-kernels with the notion of a cone. However, not everything works as nicely as before because the cone is not functorial. So with this idea in mind, I want to give you the definition or a sketch of the definition. So category T is called triangulated if it is an additive category equipped with an autoequivalence 1, which is the shift functor, and a class of so-called distinguished triangles, which is something as you see. And these distinguished triangles are required to satisfy some actions. I don't want to go into detail, but in the next slide we will see some properties. But before that, I want to say something about notation. So we have used the notation 1 to denote the shift functor, but we also need the -1 to denote its inverse. And then we use n to consider the shift n times, minus n to consider the composition of its inverse n times, and then the d0 to indicate the identity functor. So why triangulated categories are so similar to abelian ones? Well, because, for instance, given a morphism, we always have a distinguished triangle associated to it. And also the new object inserted in this distinguished triangle is actually determined up to isomorphism. So we can write C to be the cone of F. And well, as I said, this is not natural. So in fact, this is not determined up to unique isomorphism, it's determined up to non-unique isomorphism. Another very similar property to abelian categories is that a commutative square can be extended to a map of distinguished triangles. So to say, we also have maps between the cones, but this is not done in a unique way. So we see once again the non-naturality of triangulated categories. And as a last property, we have some sort of the third isomorphism theorem. So given two composable morphism, we have this isomorphism between cones. And if you use co-kernels to instead of these cones, you will actually have the third isomorphism theorem. But you can't really do this in the triangulated categories, but I think it's very good to have a grasp of the idea here. So, okay, this is the idea of triangulated categories, but of course we want to work with some examples also to understand the theory better. So the main example for us will be derived categories. So we first of all fix an abelian category, and then we construct the derived category dA, where the objects are cochain complexes. So what does this mean? Well, we consider a Z-graded object, if you wish. So we have, for for every integer, we have an object of the abelian category, and then we consider consecutive maps, and the composition of two consecutive maps will be 0. Morphisms are really hard to describe, and I don't want to deal with this. So let me give you just an idea, and the idea is that we want to invert some morphisms so that the category becomes more useful when dealing with the theory. So the idea here is to invert something called quasi-isomorphism. So morphisms which induce isomorphism in the homology. If you don't know anything about this, it's not important, but I wanted to point it out to those of you who may know. Also, I tricked you a little bit because I don't want to work with the derived categories. I want to work with bounded derived categories. So we put this B here. And the objects, we change slightly the objects, which are now bounded cochain complexes. So eventually we will reach 0 at the left and also at the right. I give you the example, but let me say something about the triangulated structure. So the shift functor, first of all, is just shifting the degrees. So when we apply the shift, we will have f0 at the degree -1, then we will have f1 at the degree 0, and so on. While the distinguished triangles satisfies the following. So we can see how triangulated categories are some sort of abelian categories, even though they are definitely not. So for every short exact sequence on the abelian category, we will have a distinguished triangle in its derived category. Before going on, I also want to talk about the functors between triangulated categories. So to recall the definition, triangulated categories have shifts and distinguished triangle, and also they are additive. So first of all, we want the functor to be additive. Second of all, we want it to commute with the shift functor, and this can be done via a natural isomorphism, which is very important because it also tells us how f sends distinguished triangles to distinguished triangles. As you can see here, phi appears. So now that we have described the framework, we want to talk about the main objects we are interested in, the exceptional sequences. So the idea is that we want to give a description of our triangulated category, and we want to give it via simple pieces. And first of all, in order to give the definition of exceptional objects, we need to restrict to k-linear triangulated categories, where k is a field. So we have, if you don't know, we have the morphisms to be k-vector spaces and the composition to be k-bilinear. So now the definition of an exceptional object reads like this. We have that simply these objects don't talk to their shifts, unless, of course, we have n equal to 0, so then this shift is just the identity functor. And in that case, we are considering just the endomorphisms, and those are generated by the identity. From this definition, which may seem a little bit off, we don't really understand maybe what's going on. Well, the idea is that all the extension we can create are actually direct sum of shifts of the exceptional object. So, in other words, all extensions are trivial. And here by extension, I mean just an element, an object f sitting in a distinguished triangle, as you can see. Okay. So, well, I'm not really interested only in exceptional objects. I'm interested in exceptional sequences. So let us try to give the definition of this. And actually, what we need to consider is home finite dimensional full strong exceptional sequences. A very, very long name, but I hope in this slide you will you will understand it better. I hope. So we have a collection of exceptional objects E1 and En, and we say that this collection is an exceptional sequence if we can't go back. So in some sense, we have an order. So we are going to E1 to E2, but we are not going from E2 to E1, for instance. The strongness requirement actually tells us that the shifts don't touch. So the idea is that whenever we consider a shift which is not the identity, we will have that these morphisms are 0 for every choice of I and j. The notion of full is if it generates T, and on finite dimensional is this very I don't know, chaotic requirement, but the idea is that you want to work with finite dimensional vector spaces. So why is this on finite dimensional full strong exceptional sequences so interesting? Well, because they describe very, very good what the triangulated category is. And this is the statement of Bondal's theorem. So let A be an abelian category with enough injectives such that the bounded derived category is given by a finite dimensional full strong exceptional sequence. Then we have that the bounded derived category is in fact exact equivalent to the bounded derived category of the right modules of A, where A is the endomorphism ring of the direct sum of all the exceptional objects we were considering. So actually what we are saying is that our category was already determined only by this exceptional sequence. And well, in fact, this result also holds if A is the category of covariant shifts on a smooth manifold. And if you want to read the Bondal article about this, you will see that he states this for the category of covariant shifts, and then he explains how the proof can go for abelian categories with enough injectives. But I thought, as we are in a categorical symposium, it was better to talk about abelian categories instead. Our aim now is to generalize this theorem for well, more general triangulated categories. And well, it's not the first time someone has done this, because we already have a generalization, in fact, and it is given by a result of Bernard Keller. But it was explicitly written only by Orlov, I think 6-7 years later. So that's very interesting, I think. And this statement now holds also for algebraic triangulated categories. But what are they? Well, first of all, let me say that this notion of triangulated categories really covers every example you may think of, almost every example. And the idea is that we can adjust the non-functoriality of the con by expanding morphisms and then quotient and then use a quotient in order to get our triangulated category. I don't want to go into detail, but it is very important to notice that all locally small derived categories are algebraic. So this is in fact a generalization of Bondal's theorem. So now that I covered this part, we can finally get to the compatibility. So as you may think from the title of this presentation, compatibility here means compatibility of T structures in a semiorthogonal decomposition. So we need to define what T structure is, what semiorthogonal decomposition is, and then finally say what the compatibility is and state a proposition about it. So let us start with T structures. As we are working with bounded derived categories and some sort of bounded triangulated, we want to focus on bounded T structures. And these bounded T structures are actually determined by their heart. So instead of telling you the definition of T structure, which may be a little bit misleading or also incomprehensible, I just give you the definition of a heart. So a heart of a bounded T structure is an abelian full subcategory A containing T, such that, well, it doesn't talk to its negative shifts. So whenever we have a morphism and this shift is negative, we will have 0. The morphism will be 0. And the second property is that A, in fact, generates the whole triangulated category. And of course, an example is needed here. And the very important example is that the abelian category is always a Hart inside its bounded derived category. So this is very important. And now that I described what these structures are, we can go to semiorthogonal decomposition. So a semiorthogonal decomposition of T is given by Chu, because I'm lazy, but you can do it also for more full triangulated subcategories. And what we require is that we can't go back, exactly as for the sequences. And the idea is that also we want them to generate. So it's some kind of sequence and full. And here we can write also we can write this situation with this notation, which actually we already encountered when we were talking about exceptional sequences. And the example here I want to point out is the following. If you pick a home finite dimensional full exceptional sequence, then we definitely have a semiorthogonal decomposition. So we see how the exceptional sequence now plays a role in this compatibility idea that we are going to show now. So we consider semiorthogonal decomposition given by two semiorthogonal components, T1 and T2, and we consider Harts on the two semiorthogonal pieces, components, if you wish. And now the T structures are called compatible if the first Hart cannot go to the negative shift of the second Hart. And the proposition, which you may expect, is that in this situation we have an associated Hart A on the whole T now, and this contains both A1 shifted by 1 and A2. And maybe some of you are wondering if it is possible to change this shift or delete it. Well, this is not possible, because if you try to do this, you end up with you are requiring just too much, and so it's better to have this shift and try to deal with this without changing it. Now, finally, we are going to state the main theorem and also see a little bit of proof, a sketch, of course. But first, we need our notion of triangulated category for the generalization, because actually it didn't prove it for all triangulated categories. We need this requirement, which I call the realized. It is a new definition, but it is very, very much linked to other older definitions that already exist. So triangulated category T is called the realized if for every Hart A on a full triangulated subcategory of T, we have a realization factor that is generally denoted with real. And this is just an exact factor that if you try to restrict to the Hart, it will give you the identity. And here I require this to hold for every Hart on a full triangulated subcategory, because I want that all triangulated subcategories of T are in fact also realized. So it is closed under subcategories. It is very important to notice that all algebraic triangulated categories are realized, and so in particular also locally small derived categories are realized. And finally, we are able to state the theorem. So let T be a realized triangulated category with finite dimensional full strong exceptional sequence, E1, En. Then we have this exact equivalence with the bounded derived category of the right modules of A, where A is as before, so the endomorphism ring of the direct sum of all exceptional objects. Now the proof is by induction. So we want to proceed by induction on the length of the exceptional sequence, so on n. And now we consider the semi-orthogonal decomposition given by S and En, where S is generated by E1, En minus 1. So now by induction hypothesis, we have that S is actually exact equivalence to the bounded Lie category of mod of A tilde, where A tilde is the endomorphism ring we were looking above, but now we have En doesn't appear anymore here. So we want to add it now in some sense. And so now the proof splits in 2 steps. The first one is to try and add the En part, and we do this via the proposition star. So we consider the natural heart mod A tilde on S, and we consider also the other heart, which is just the direct sums of the exceptional object En. And now it is possible to prove that these 2 hearts are compatible. So now by proposition star, we have a heart A contained in T. And the next step is to use the fact that now we have a heart. So we want to use the fact that T is a realized triangulated category. And now we have a realization functor. In fact, this is proven to be an exact equivalence. This is not always the case. Actually, there are many hearts that for which the realization functor is not an exact equivalence, even when you pick the nicest derived categories you want to think about. But in this case, with this construction and this induction, we actually get this exact equivalence, which concludes the proof. And okay, this was my presentation. Thank you for your attention. And if you have any question, please feel free to ask. Here are some references of the older statement.
Thanks, Antonio.